Can hear me well? Okay, so today we will have the presentation by Dr. Lukman Noerochim from ITS Indonesia. So first of all, let me check whether you guys can hear me clearly and whether you guys can see the slide. I'm not sure whether you can send me any chat message here. Okay, so I believe so the audience can hear me, so it's maybe they can hear you as well. Okay, so now will leave the stage here and then give it to back to Dr. Lukman. So please enjoy his presentation. So now the stage is for you, Dr.
Okay.
Lukman. Go ahead.
Yes. Yes. Okay. Thank you for Rajana for this event. So please first I want to introduce myself. My name is Lukman Noerochim. I am from Battery Group Department of Material Engineering, Material and Metallurgical Engineering, Faculty of Industrial Technology, Institut Teknologi Sepuluh Nopember, Surabaya, Indonesia. I think all audience maybe already heard about the Indonesia, right? But maybe not for Surabaya. Surabaya is the second biggest city in Indonesia after Jakarta. So this city is located at the east part in Indonesia, close to Bali. Yeah, maybe Bali, everyone familiar with this beautiful iconic island in Indonesia. So welcome in our session today. I am happy here to share with you all for this event organized by Prof. Rojana with ECS session and then for eAsia Respect scheme for this year. So yeah, we are in ITS, yeah, Institute Teknologi Sepuluh Nopember have already researched very long time for especially for lithium-ion battery since 2013 after my graduation from PhD program. So we have many facilities to do this kind of research, yeah, for lithium-ion batteries, sodium-ion batteries, and now we are also working for recycle batteries, spent batteries with Prof. Rosana and Prof. Soratep from Chula University. So for this session, I will share with you about our recent research about the cathode or lithium-ion batteries. So the title for my presentation today is about the new type of cathode. Then namely is NMA, and this from actually from nickel mangan aluminum. So yeah, so why I select this kind of cathodes? So I will briefly introduce you some information on the background for this research before we the next slide. So yeah, now we are in electrical shift to electrical transportation era. So many countries in the world they starting to convert or replace the conventional engine, or let's say a combustion engine, internal engine, by using electric vehicle right now because due to the emission and the climate change, global warming, that now we are already faced it in this year in Indonesia, right now, especially in Surabaya. This summer is very hot, yeah, compare a couple of years ago. So and the rainy season lately is a little bit late, yeah, for this year compared to last year. So we are already the same problem. I think I don't know in Thailand also have the same climate in like Indonesia or not for the day, for this year. So that's why people right now many manufacturing electric vehicle or maybe in the popular manufacturing they already start to produce or fabricate for electric vehicle, and the goal is the first is to get long distance range of this vehicle at least for standard, or maybe for the goal is for reach until 500, or maybe in kilometer is maybe around 1000 or maybe around 800 kilometer for single charge. Yeah, for single charge they can hopefully for this the reach for the goal is for this car electric vehicle. So many global manufacturing they start to produce this kind of vehicle, like this picture from Lucid Air, yeah, starting from the price of $150,000, and then the distance that can be reached until 515 miles. So this is maybe around 800 kilometer for single charge. It's quite incredible. Yeah. And then the second one is Tesla Model S Long Range Plus. That the price is from 7,000, 4.900 that can be reached until 402 miles. And then the third one is Porsche Taycan Turbo S with the price more expensive than the second the two of car. Then, but the distance only 192 miles. So this is in 2020, but I think the technology I think right now is already reached this goal for the long distance of the electric vehicle. So let's see from the next slide. Let's see more on the in 2023, the longest range of EV is still owned by Lucid Air. In 2020, they claim over there that see here in this the real right now this the first, yeah, that we can see in the first position still owned by Lucid Air, Tesla, and the second is Tesla model and Hyundai Ioniq for the third one. And for the and for the production, yeah, global EV sales, even Lucid Air is the new model, but the competitor is still BYD, yeah, and the second one is for Tesla. So the estimate global plug-in electric vehicle sales in the first half of 2023, the BYD is the first position with 1,000 around 200 million vehicle, yeah, and then the second one by the Tesla. So in this year, BYD already conquered the Tesla for the first position of the production for electric vehicle. The third one BMW, and then the third one is Ion from China as well. Volkswagen, SKM is from China as well, and then Mercedes. So we can see here, China manufacturing, they already have four big for the manufacturing for electric vehicle right now. So in Indonesia, the BYD also already come into our market. Yeah, they already launched maybe 3 or 4 model. They already in commercial market Indonesia previously by Wuling. Yeah, Wuling actually the first commercial electric vehicle that already in the market in around 2022 or 21. They already enter in the market in Indonesia, and this year then BYD enter, and then next maybe Ion, yeah, and maybe many magnet brand from China. They already have some already enter to Indonesian market. So the first question is still about the batteries that we have. We know that the batteries is the main component for electric vehicle. We know that, and then the price also the batteries will be spent on maybe around 30% or almost 50% of the total budget for total price for electric vehicle. So if you are buy electric vehicle and when you need to replace the engine or maybe in here the battery, so you need at least half of the price to replace this. And this is still quite expensive for many people, yeah, especially Indonesia as well. So still research try to the best to find, yeah, the best candidate for batteries, yeah, especially for cathode. And right now, you know that at least three kind of cathode in commercial already in commercial market. So how there is first is LFP, lithium ferrophosphate. The second one is nickel, mangan, cobalt, NMC, and the third one is nickel, cobalt, aluminum. So this is the already commercial that already applied to electric vehicle right now. Like Tesla, they use NCA in the first production, and then ship to NMC, and then the last report that they want to change to LFP due to concern about the safety concern about the electric vehicle. And we also consider the LFP maybe for the next, yeah, technology because the cost, yeah, the cost LFP is more cheaper than NMC and NCA, yeah, compared to other. Then even the energy density is much higher for NMC and NCA, but the concern about the thermal runaway and then the concern about the safety is still most important factor that people want to buy the electric vehicle right now. So yeah, okay, for energy density, NMC is still the strong candidate for the future technology because they have the highest energy density. And but you know that some of problems, so people try to improve, yeah, so still to improve the safety and then the reliability capability of this cathode. And another concern about the cathode is about the raw material. We know that for the NCA and NMC, most of the cathode is precursor from like nickel and cobalt and mangan. And this is we say that this is like a rare, yes, this is very uh, uh, small deposit in some countries. But so the people afraid that some this support the supply and chain will be have a problem for the next year. And we see here from start from 2000 and right now in 2016 the demand of the raw material ore or multi omit that imported from Republic Congo, special for cobalt. Cobalt, the largest deposit in the world, around maybe 60%. Cobalt is in Congo, and Congo, and the problem is right now they have still a political problem, not stable right now. So people afraid that this will be effect on supply chain for the raw material. In Indonesia, you know that Indonesia also have the high deposit for nickel. We have the first, yeah, maybe in the first country that we have a very high deposit of nickel. This location at Sulawesi Island, um, the precisely in Morowali, yeah, the Morowali area. This column we have Morowali, and there are some industrial park over there. We call it as Indonesian Morowali Industrial Park. Yeah, and many factory that they are concerned about mining to nickel and then process it into precursor, some of this to nickel sulfate for precursor of the cathode of NMC. So still people concerned about this supply unchain, and the will be effect on the lithium-ion battery production, and the cobalt supply deficit is forecast early in 2030. So that's why researcher in the world, they try to replace or increase the content of nickel, or maybe replace the cobalt by others element. And this is the story and or the timeline evolution of the nickel-rich cathode material from low to high nickel content. Actually, already start at 1991. Yeah, 1991 from Liu. Yeah, they start for MCM 721 and CM 622, and then up to now into uh, 2019 by ISOFA, and they already present about the redefine the rule of the mangan in the nickel rich nickel cobalt mangan cathode. Okay, so this is the timeline that already people try to replace to increase the content of nickel due to the concern about the cobalt supply chain. And right now in the market we already have several type of NMC that people already familiar with this, with NMC 111, yeah, with the composition of nickel manganese cobalt around 33%. And then the second type of NMC is 622, yeah, but the nickel is 60% and already increased. And then the last one is NMC 811. This is the highest right now, the highest content of nickel, yeah, in NMC cathode. Sorry. So in the last couple, maybe last year, people already also try to increase up to 90%, 90% of nickel. So people said this is a new type of NMC. People said this is people 0.5, 0 point something, but maybe not really published. Maybe we're not really familiar with this kind of type of cathode. So people concerned about still to import the NMC 811. Now if we want to replace cobalt element with others elements, so what candidate? Yeah, so what element should be the best candidate to replace for the cobalt? So people concern aluminum. this is a metal. But from the previous result, like NCA, so aluminum to be the best candidate for replacing the mangan. Sorry, for cobalt. And general strategies for enhanced performance of electrode. This is a general strategies that some of already people believe that even they can do to improve their electrochemical performance, like dimension reduction, composite formation, doping, and functionalization and morphology control. So by using doping like aluminum to replace the cobalt, so research try to improve the electron and ion transport, to replace the cobalt. So this is some of the, so we are in 2023, last year. So maybe before that we start to synthesize of this cathode NMA. We call it as NMA. People also know this one. So by using similar method in NMC preparation method, that we use nickel sulfate and then manganese sulfate, and then we replace cobalt sulfate with aluminum nitrate, and using acetylating again with ammonium, and then sodium hydroxide, and we are using this kind of apparatus facilities in a big tank to synthesize or prepare for the product of NMA. So in this kind of method, we have to very careful to set up of this kind of apparatus to make sure that the especially for nitrogen gas here should be mixed well, yeah, in the solution, because we know that this especially for mangan and then aluminum nitrate, they very easy to oxidize. So if you are prepared for this kind of methods, to make sure that nitrogen already have mixed well by bubbling for several times in the reactor tank for this kind of preparation. Another thing that we have to consider of this preparation, that the volume, the volume, even we are already calculate the stoichiometry, people said maybe I want to try very small, yeah, because our limited precursor in the lab. In our experience, so that if we are only prepare maybe 100 milliliter or 200 is not enough, yeah. So sometimes we fail, we cannot get the correct phase for this kind of NMA cathode. So that's why people or researcher in the paper, they synthesize this method, this matter in a big tank, maybe 2 liter, yeah, 2 or 5 liter. So this is why we suggest you, if you want to synthesize, so you have to prepare more than 1 liter, yeah, to synthesize this material. And then after we prepare this is for mix around 10 or 12 hours. We have to control the pH, yeah. For the pH should be around 11.5 or maybe more than 11, but below 11.5. So this is very sensitive factor that we have to consider to do this experiment. So we have to control very careful for this pH, yeah, to control the pH. And also speed motor the RPM, this has effect on the morphology and the particle size. That also we have to make sure, because the solution will be more thicky, yeah, after 2 or 5 hours. Then the power of motor should be enough, yeah, to rotate the plate or impeller inside of this reactor. So after we are finishing around 10 or 12 hours, so after that we are filtering this solution, and then we got the green color, yeah, green color, and then the green color will be transferred to process calcination. Yeah. For the calcination, in this we use oxygen gas, yeah, environment, then to improve, yeah, the crystallinity of our processor, our powder. So the calcination usually in high temperature, this around 800. In our experience, we use 800 degrees Celsius for around 10 or 15 hours. And I suggest you to make sure to control the volume rate of the gas, yeah, because it will be effect on the smoothness, or maybe in the surface, yeah, the surface of the particle. Okay, after that finish, then we will cut the as prepare material for NMA. So for this preparation, we make three variation, yeah, for the concentration of the aluminum. Yeah, I can show you later. So the three variation here is NMA 991, NMA 973, and NMA 955. So based on this XR, we know that the peak is similar, matching with the GCPDS number 01, 09. And for the most important when we are analyze the XRD is the ratio between the peak 003 and then the peak intensity peak of 104. People consider the ratio between this peak should be more than 1.2 to uh, to hinder, yeah, to make sure there is no lithium nickel mixing. Yeah, so this is a kind of phenomena that people researchers said this is a lithium nickel mixing. If the the ratio should be more than 1.2, yeah, in this case. So we can see here that the variation NMA 973, they have the lowest Le nickel mixing because the ratio is more than 1.2. So another thing is about the ratio of the lattice parameter, special for C and A. If the C and A is will be enhanced, the space in crystal structure of this hexagonal crystal structure for NMA to improve the flow or the diffusivity of the lithium ion during such discharge process. So this is the two factors that we have to consider when we observe the XRD for NMC, especially for NMC, NCA, NMC, NMA. This a family. We have to consider about the lithium nickel mixing phenomena in this kind of material. So next, after we analysis of SRD, now we are going to the SCM image that for this, we know looks like this kind of material they have a similar particle size, but when we assess by using in image C, that we see the particle size around 200, 200 or something in nanometer. That for NMA 973 maybe around around something 200 nanometer. So that's why it's quite difficult to differentiate between them, but we can see that this is quite similar. So we want to do PET, but unfortunately, the PET facilities in our institute is broken, so we cannot use until now. And now we're going to see the CV, cyclic voltammetry behavior, that for all these specimen they have a similar, that they have a phase transition from reduction and oxidation. From the oxidation we have the phase transition from hexagonal H1 to M. M here is monoclinic, and the first peak for oxidation, and then the second peak is monoclinic to the second hexagonal, and then the third peak in oxidation swap, they have also transformation from H2 to H3. This kind of phase transition also back to by using reduction peak, that we know that for H3 also is similar for oxidation, and the separation for between this kind of oxidation and reduction, we observe that for NMA 973 they have a smaller distance or potential delta for reduction and oxidation. And we are now going up to the electrochemical performance that our control. Now this is so this is the first. The A is typical charge discharge curve for NME here. That this is for the range is from 2.8 to 4.4 volt, and we use 0.1 C here. That we observe that there are a slope here at around 3.8 for the Windows working Windows for this kind NMA. So this is quite high compared to LFP. LFP is around 3.2 or 3.4 something. So this is the typical characteristic of the NMC, that they have the higher working voltage compared to LFP. So in the curve of P, this is the curve after several cycle, or maybe no, this in 1C, So in previously in 0.1C we have a discharge capacity For the highest capacities is belong to NMA 973 with around 170 milliampere hour per gram, and then we increase the current density to up to this in picture number B, and they have decreasing from the voltage window from the curve because the effect of the kind of high current. And the stability, the cycle ability of this sample, they look similar between all these sample, but for NMA 917, they have the highest capacity up to 100 cycle, and they still maintain the capability. And the capacity fitting is around 80 or 85%. So we see in the last picture, in this number D, we do some variation of C rate from 0.1C till 5C, and with the highest C current, these samples, they have still maintain the capacity for NMA 973 is around 100 milliampere hour per gram. So if we are compared to commercial NMC like NMC 811, so the specific discharge capacity for this sample, special for NMA 970, still below for the commercial NMC. NMC, this example NMC 811, they the specific discharge capacity is around 200 milliampere hour per gram. So even our discharge specific capacity is lower than NMC, but they still have opportunity and they have chance in the future to improve the electrochemical performance to achieve more higher than right now, and still going for research to improve this capacity or to reach the goal at least similar with NMC, commercial NMC. And for to analyze more about the conductivity, we also do for IES, electrochemical impedance spectroscopy, to observe the characteristic why this kind of material have electro performance that we can see in the previous slide. So for NMA 973, the characteristic like semi-cycle with low frequency and have Warburg impedance and high frequency and then low frequency for Warburg impedance that we can see in equivalent circuit. We attach to this picture that for the NMA 917, they have lowest resistance charge transfer compared to others sample here. And for the lithium diffusion, shown that for number B, picture number B, an sample 973 also have the highest lithium coefficient for this material. Okay, so this is our recent research about the experiment for NMA. So we are still going to improve this kind of material to improve the steel stability and increase the discharge capacity. For the research, I want to thank you for ITS for the funding for this research. Thank you for Prajana. I will back to you for this session. Thank you very much for your attention. See you later. Maybe go to next session.
Okay, so thank you very much, Dr. Lukman. Very impressive work. Okay, so probably right now, we'd like to open the forum, right? For if you guys have any question, please feel free to type in the chat, and uh, and then I will ask Dr. Lukman. I'm not sure whether Dr. Lukman can see the chat.
Yes, I can send the chat. Yeah.
Ah, okay, okay, okay. So please feel free to send question in the chat. In the meantime, probably I will ask you. So, what will be the next possible composition that you think that is could further improve, or do you think that you need to add more elements into the your NMA cathode?
Yeah. Okay, thank you, Professor. So we are still focused on this NMA 973, but we want to improve the conductivity because from
Mm,
the ACE measurement, we see that the charge resistance is still high. So right now we have a student to do this research by maybe by coating with maybe with carbon or maybe with graphite or maybe other conductivity agent to improve the conductivity of this material. If we want to add more doping, for example, from my experience, this kind of material is very sensitive to other elements. Sometimes they can improve their electrochemical performance, but sometimes will be decreased because the lattice parameter will be sensitive for the lithium-ion diffusivity and then conductivity also will be usually very sensitive for element doping for this kind of material.
I see. Okay, but your stability is quite impressive, though.
Yeah,
I like.
but and this is only for 100 cycle, but maybe we need more. Right? We need more than 100.
Okay. Oh, but Dr. Luman, there is a question in the chat.
Yes, please.
So it said, can you give more explanation about electrochemical performance of your synthesized NMC versus the commercial NMC 111?
Yeah, we are sorry, we're not synthesize NMC, but we synthesize
Probably you mean
NMA.
NMA, yeah,
Yeah.
NMA versus the NMC 111.
Okay, if we see commercial NMC for 111, we know that this composition is around 30% of nickel, 30% of manganese, and then 30% of cobalt. Uh, People, okay, this is very good electrical performance right now. Because we know that the contribution of mangan, especially cobalt here is very important to improve the especially for capacity, yeah, capacity and stability. But in previous slide, I said that this about the supply chain, yeah, for the cobalt right now is very sensitive or very maybe couple years, next couple year, 10 years, the cobalt element will be more difficult, yeah, to find because maybe only in the Congo, yeah, the Congo, the mining of this element. So this is, we can say this is very rare earth, yeah, rare element. So the price will be more expensive. Yeah. Even the NMC one is more is very good and stable electrochemical performance. But if the price is very expensive, so people will cannot afford to buy or to purchase this battery. So will affect on the price for the electrical vehicle. So yeah, this is also we have not only consider for performance electrochemical performance, but researcher also we have to consider the economic, yeah, economic factor, economic scale for most mass production. Okay, our material is good, everything is good, but if people cannot buy, so it's cannot people cannot feel or maybe use this cat or material, and the market will be loose, yeah, lost. So that's why right now we try even our electrochemical performance NMA is still lower, yeah, than the NMC 11 commercial, but the next future is more comprehensive or more bigger, because we know aluminum is very easy to find, and many countries we can find this element. Nickel also we have many deposits, so people not really worry about the supply and chain. Also manganese okay, no problem. Yeah, so that's why we improve, want to synthesize this kind of material. That's it, Surzana. Yeah.
Okay, thank you. So basically, the performance is still doesn't match the NMC 111, but
Yes.
to
Yeah.
the supply chain. So there is a chance that it may be more possible, right, for the
Yes.
large
Yes.
scale manufacturing, right?
Yes.
Okay. Oh, but I want quick comment. And how about the comparison with the lithium iron phosphate?
Oh yeah. For lithium iron phosphate is we know this cathode is more cheaper, more
Mm,
stable, yeah, more and safety constant they are so more stable than NMC. But we know the energy density LFP is lower than NMC. So that's
mm,
why um, people right now is concerned about safety, because many accident relate with the electric vehicle in China. Maybe you know very many video, yeah, in YouTube. They accident suddenly explosion, yeah. Not people will be not aware, so will be many injuries or maybe lost, yeah. So people right now concerned about this for the safety. If
mm,
the safety is not guaranteed, so people will not buy the electric vehicle. Maybe will be afraid. Yeah, maybe very worried. Oh, this will be explosion. Maybe make fire. So will be, yeah. So that's why for the next technology, uh, manufacturing and many even Tesla also they ship to use LFP for their battery, and also for BYD. You know BYD, I saw you in the last two slides before. So they use a technology what we call is split, yeah, split batteries. That the inside they use also LFP for the cathode. So right now electric vehicle ship to use LFP for their batteries. Yeah.
mm. Okay. But can you compare performance of your NMA with
Yep.
the LFP?
Yeah. For the
To be
NMA,
more
I
superior,
still, yeah. For the NMA, I still not about to find this to set the research about the safety concern, but thermal runway or maybe short circuit for the NMA. People said this. The latest research, latest paper said that NMC is more safety than NMC.
right?
Maybe also compatible with the LFP, yeah, comparable with the LFP. And we know this is will be promising. I think the NME for the next candidate
Mm,
for replacing for the cathode, yeah, for safety and energy density.
okay. Okay, thank you. Is there any other question from the audience? It's feel free to type in the chat. Or can you have a quick comment on the recycling ability of your NMA? So it will be
Yeah,
easy to recycling or about the same, like I mean, but it look like the same process, right? I'm not sure
yeah,
about the aluminum, like recycling of aluminum component compared
yeah.
with cobalt component.
Yeah, for recycling, I think in for NMA also more easy. I think it will be more, not complicated that because this element is very common. Yeah, that mangan and then nickel and then aluminum that we can maybe do separation or maybe we can using extraction for the
I
element
see.
using, yeah. But for the direct method, we not any experience, yeah, to recycle or to regenerative, yeah, regeneration method for this kind of batteries because there is no commercial cathode for this until now. Yeah.
Okay.
So still NMC, LFP, and LCO maybe the commercial cathode will be used for the couple years, the next couple years. NMA, I don't know, will be commercial or not. But
I
I think
see.
from the recycle, I think is possible. I mean the chance to recycle also have opportunity, big opportunity to recycle this kind of batteries.
Okay. I think I have one last question for myself. So
Uh,
about the synthesis process, you use co-precipitation. I mean, do you think the process can influence the performance of your NMA? Like, is
yes,
there any way that you can further improve your synthesis process as well?
yes, yes, of course. So many route to synthesis of NMC and people maybe can select co-precipitation. People also others method using hydrothermal, yeah, and then maybe solid state method. But
Mhm.
mostly research and manufacturing, or maybe global factory like Kettle, like LG, Hyundai. They use co-precipitation to synthesis of this material. So in our experience that like pH, yeah, and then the nitrogen environment and then the RPM when we are mixing will very effect on our quality of our product. So I already explained in the slide that this is very sensitive factor that we have to very careful to do this one. Yeah.
Mm, I see. So still several parameters for the
Yes,
synthesis
yes,
that have need to be optimized. Like,
yes. That's right. Yes.
I see. I think that would be all for today. So since there is no further question from the chat, so let's thank the speaker. Thank you so much, Dr. Lukman, for the talk
Okay.
today.
You're welcome. Yeah.
Okay,
Thank
so
you,
I think that
professional.
that would be all for today webinar. So please keep continue like register for our series. Like we have webinar series
Yes.
almost every Monday afternoon. So I will keep posting for
Okay.
PR, and I also send you like Dr. Lumen. Please feel free to send to like any interested researcher in Indonesia.
Yeah,
So
yeah.
next week I will invite Dr. Nurak, like Professor Nurak from Thammasat University. He will talk about his lithium-ion battery recycling that he
Mm.
already like upscale that
Mm-hmm.
lithium-ion battery
What
recycling
next
system.
week?
Next week, same time,
Okay. Same
3
time at 3
p.m.
p.m.
same time as
Okay,
right,
okay.
3 to
Okay.
4
It
p.m.
will
I
be
will prepare the
interesting. Yeah.
poster and then PR again. Okay,
Yeah.
thank you very much, and thank you all the audience. Okay. Bye
Okay,
bye.
thank
Thank you so
you.
much, Professor.
Okay. See you. Bye bye.
I will
Everyone.
end
See you
the
next
session
time.
now. See
Yeah.
you.
See you. Bye.
Bye.